Hello everyone, welcome to the class U18 PCAE 601 Finite Element Analysis. Myself Mr. N. Kalaimani, currently working as assistant professor in the Department of Aeronautical Engineering, Bharat Institute of Higher Education Research, Chennai. Today we are going to discuss the topic of one-dimensional bar analyzed by finite element analysis. So as a design engineer, if you design any structural components, the structural components should be capable of to withstand what are the loads imposed on it. Therefore, as an analyst, we need certain requirements while designing or assembling of parts of the product. Here I listed some of the few requirements. One is displacement certain points, stress distribution, natural frequency, critical buckling loads, vibration. Suppose if the physical phenomena expressing the flow field problems, then we need to analyze pressure, velocity, and temperature distributions. Suppose if it is subject to any cycling loading conditions, then we have to calculate crack growth, residual strength, and fatigue life. Once if we know the requirements, then how we'll do the analysis? There are three methods of engineering analysis. One is experimental method, analytical method, as well as numerical method. In these following methods, engineer always prefers numerical methods. It will use approximate solution, but it is an acceptable one. So in this numerical method, under following three methods comes to numerical method. One is function approximation method, finite element method, then finite difference method. If you go for in this lecture, we will talk about one-dimensional bar analysis by finite element methods. If you go for finite element method, we need to follow some general steps. One is we have to describe the structure into convenient number of elements. Then we have to assign node numbers as well as elements. Then third one is we have to develop a finite element equation for individual elements. Then we have to assemble, we will get a global finite element equations. Once we get a global finite element equation, then we have to apply your essential boundary conditions. After applying essential boundary condition, we will get some simultaneous equation. While solving the simultaneous equation, we will get the solution of the problem. Maybe all these three cases, first thing is we have to express a problem into a differential equations with well proposed boundary conditions. What is meant by well proposed boundary value problems? If the problem is exposed in terms of well proposed boundary condition, then there is existence of the solution and also uniqueness of the solution. A small perturbation in the boundary condition should not result in large change in the solution. So what are the possible types of boundary condition available for a two-dimensional problem? One is a Dirichlet boundary conditions or essential boundary conditions. So value of the dependent variable specified at the boundary is called as a essential boundary condition or Dirichlet boundary conditions. Second one is Newman boundary conditions. So if any boundary conditions is expressed in terms of your gradient of the dependent variable, then it is called as a Newman boundary conditions. Then mixed boundary condition means the value of the dependent variable is expressed as a function of gradient, then it is called as a mixed boundary conditions. Then I would like to ask one question. If any condition associated with the boundary is a boundary conditions. I would like to answer this question with this example. Let us consider a one-dimensional steady-state heat conduction with no internal heat generation and also assume a uniform thermal conductivity. Here, the both end is specified heat flux. The rate at which entering is 1 watt per meter square. According to steady-state conditions, then rate at which heat leaving also Q is equal to 1 watt per meter square. Both end is specified Newman boundary conditions. It is a one-dimensional steady-state heat conduction problem. We know the differential equation. That means d square T by dx square equal to 0. This equation 1 we have to integrate 2 times. We will get the temperature equation T is equal to C1x plus C2. Now you apply your boundary condition. What is the boundary conditions? They specify the heat flux at entering Q is equal to 1 watt per meter square. According to Fourier law of heat conduction, the heat flux is Q is equal to minus K times dt by dx. Therefore, if we are assuming here thermal conductivity of the material is 1 watt per meter Kelvin, then minus K into dt by dx equal to 1, we have to apply K values to 1, then we will get dt by dx values minus 1. Into applying, if we differentiate equation 2, then we will get dt by dx. Then we have to apply our boundary condition. Then we will get C1 values here minus 1. And finally, the X is equal to L also, the Q is equal to 1 watt per meter square. If you apply this condition also, we will get same C1 values here minus 1. Then we are at temperature equation. Finally, we return T is equal to minus X plus C2. So based on the C2, we have different type of solutions. So I already told that if the problem is exposed to well-posed boundary condition, it will use only uniqueness of the solutions. But in this case, we have a many number of solutions. But we have a solution, but the solution is many number of solution depends upon your C2 value. Suppose if any condition is specified, the boundary condition is here, not a boundary conditions. If it is a want to find out the temperature distribution of the rod, here at least 180 we have to specify the essential boundary condition. Essential boundary condition at any 190 we have to specify the temperature. So if you consider say a bar having uniform cross section and it is subject to axial load F, we know the differential equation AE times d square U by dx square plus body force Q is equal to 0. In this one end is fixed, then we have to substitute x equal to 0 as well as u equal to 0. This end is a boundary condition specified in terms of field variable or dependent variable. Here where ultimate aim is to find out axial displacement. Therefore, u is a field variable. Therefore, one end of the boundary is specified in terms of field variable. That means x equal to 0 and as well as u equal to 0. Then it is called as a essential boundary conditions. I look at other end. This means the free end it is subject to axial load F. Then F equal to we know the EA into du by dx when x equal to L. So in this case, the boundary is specified in terms of the gradient of the dependent variable. Then it is called as the natural boundary conditions or Newman boundary conditions. We need not to apply these conditions because that's why it is called as a natural boundary condition. We need not to force to apply. Therefore, here I gave the thumb rule. If you have a physical structure can be expressed the order of differential equation 2p, where the boundary condition varies from 0 to p minus 1, it is called as a essential boundary condition. Where the order of the boundary condition varies from p to 2p minus 1, it is called as a natural boundary conditions. So first thing is we have to go analyze a one-dimensional bar element by finite element analysis. Therefore, we try to formulate a finite element equation by Galerkin approach or strain energy approach. In this lecture, we will talk about Galerkin approach. Consider a bar having uniform cross section and it is subject to axial load F. One end is located x equal to 0 where the nodal having displacement u1. The other end is x equal to the node 2. It has a displacement is u2. Therefore, we consider a small infinite segment element. Then we apply the equilibrium equation summation of force at x equal to 0. It is considered a small segment length at dx, where the force is in the right hand side f of x plus dx, right hand left hand side f of x, where the body force is q of x into dx. Then we apply, then we will get the q is equal to minus df by dx. Then from that we will apply that equation. We will arrive d by dx, where f of x is to be a force. According to Hooke's law, when a material is loaded within elastic limit, the stress induced the material is directly proportional to strain. That's proportionality constant we remove Young's modulus. Therefore, stress sigma is equal to E into strain. Strain is nothing but change in dimension by original dimension that can be expressed du by dx. Then sigma is equal to capital E Young's modulus into du by dx, where stress is nothing but force by area. Then the force equal to area into E into du by dx. That's we have to written here. Therefore, d by dx equal into EA du by dx plus q equal to 0, where q is a body forces that will be referenced as a rho g times A is equal to 0. Finally, we arrive the differential equation AE into d square u by dx square plus rho g A equal to 0. This is your governing equation for one-dimensional bar element. Then if a one end is fixed, then we apply x equal to 0, y equal to 0, u equal to 0. Then it is called as an essential boundary condition. The other end, we know that if you applied any force, then a force can be written as F equal to A into du by dx. At x equal to 0, it is called as a natural boundary conditions or Newman boundary conditions. If the first step of formulation of finite element equation, we have to derive the shape functions. I already told that it's a mathematical expression. It will tell us how the field variable varies inside the element. So we go for finite element analysis. We use linear based trial solutions. Then we assume a trial solution u is equal to a1 plus a2 x. We have two constant. We need two boundary condition to find out value of a1 and a2. The first boundary condition when x equal to 0, that is displacement u equal to u1. When x equal to L, the displacement u equal to u2. By applying this into your assumed trial solution, then we will get u1 equal to a1. Similarly, a2 is equal to u2 minus u1 by L. Then we have to apply the equation u is equal to a1 plus a2x. Then finally we arrive u is equal to 1 minus x by L times of u1 plus x by L times of u2. We compare this equation u is equal to n1 u1 plus n2 u2. We will get the value of n1 and n2, where n1 is equal to 1 minus x by L, where n2 is equal to x by L. Where n1 n2 are called as a safe functions. So what is the property of safe function? At one node, the safe function will be unity. Other nodal locations will be 0. Let us consider nodal location 1, x equal to 0. We apply n1 values equal to 1, n2 becomes 0 at nodal location 1. Suppose if you consider nodal location 2, what is the condition? X equal to L. We apply, then we will get n1 value equal to 0, then n2 value is equal to 1. And also the summation of safe function will be unity. We add n1 plus n2, we will get 1. If it is a one-dimensional element, then we have to the summation of partial derivative of a safe function. That means dou n1 by dou x plus dou n2 by dou x. That value must be equal to 0. So here we get the safe function value n1 is equal to 1 minus x by L, then n2 is equal to x by L. So once if we get the safe function value, we go for a Galerkin approach. What is a Galerkin approach? Integral over n1 times R is a residual function. That means approximate solution of your given differential equation times into dx equal to 0. If we see that you are given a differential equation in the second order, so we have to assume at least quadratic based trial solution. By we go for integration by parts formula, we need reduce one order of the differential equation. That's why we choose to here linear based trial solutions. Therefore, integral over 0 to L n1 times what is the differential equation EA into d square u by dx square plus rho ga times into dx equal to 0. Then you apply your Whiting functions to be chosen as your safe function. Therefore, n1 times EA into du by dx where 0 to L minus integral 0 to L EA du by dx to dn1 by dx times dx plus integral of 0 to L n1 into rho ga times dx equal to 0. The first second derivative of the differential equation only you have to apply integration by parts formula. That means integral of u dv is equal to uv minus integral v du. Then we will get the equation. Then we apply n1 times EA into du by dx. Then x equal to L condition. When x equal to L, it is specified at nodal location 2. At nodal location, the safe function n1 value becomes 0. If it is n1 EA into du by dx when x equal to 0, that will be indicates nodal location 1. At this location, the safe function n1 value is to be unity. That's why we will get minus EA into du by dx when x equal to 0. The same way, n1 EA into du by dx when x equal to L, the n1 value becomes 0. That's why we left that term. Then plus 0 to L rho ga into 1 minus x by L dx equal to this minus term that come to that side, we will get positive. Then 0 to L EA into du by dx into dn1 by dx times dx. Then how we will obtain du by dx? We already know u value is equal to 1 minus x by L times u1 plus x by L times of u2. Then we have to differentiate with respect to x. We will get du by dx value, where n1 should be safe function at nodal location 1. This value is here 1 minus x by L. If you differentiate with respect to x, dn1 by dx equal to, we will get minus 1 by L. We have to apply this above equation. We arrived equation number 2 minus EA into du by dx and x equal to 0 plus rho ga L by 2 EA by L u1 minus e2. So similarly, this case 2 we have to choose a safe function n2 value. Then we have to integrate. Then we will arrive equation number 3. Then we are doing this integration. We get a value of n2 EA into du by dx at the x equal to L condition. Then the n2 value is unity because it is specified at nodal location 2. Suppose n2 EA into du by dx and x equal to 0. It is specified at location number 1. According to properties of safe function, that nodal location value, the own safe function will be unity, other nodal location will be 0. Therefore, when x equal to 0, the safe function n2 value becomes 0. We have to apply. Then we will arrive equation number 3. Then the same way we have to obtain du by dx and dn2 by dx value. We substitute, we will get equation number 3. What is equation number 3? EA into du by dx x equal to L plus rho g AL by 2 EA by L minus U1 plus U2. We see that combine equation 2 and 3, we will get EA by L 1 minus 1 minus 1 1, the nodal displacement U1 U2 equal to minus EA du by dx when x equal to 0, then EA du by dx when x equal to L, then rho g AL by 2 1 1. We will arrange it in the matrix form. Then we know that the first term is EA by L 1 minus 1 minus 1, indicate your stiffness matrix. Then minus EA du by dx x equal to 0, it will indicate your force equation. Then we replace force, then it will indicate your geometric loading conditions. Then rho g AL by 2 1 1 indicates a body force. This is equation number 4 is indicates for finite element equation for one-dimensional bar element along with body forces. You consider also, we assume the Young's modulus also constant. It means the element is made up of same material, as well as area of the cross section also to be uniform. If we consider element, the area of the cross section to be uniform, then only we have to apply equation number 4. So once we derive the finite element equation, we try to solve some numerical problem. For consider the assembly of 2-bar element as shown in figure. Determine the nodal displacement, element stresses, and the reaction forces. Here the given structure is described into 3 elements. Element 1 consists of node 1 and 2. Element 2 consists of node 2 and 3. Element 3 consists of node 3 and 4. Then what is your finite element equation for one-dimensional bar element? We derived the previous slide. That means AE by L 1 minus 1 minus 1 1 U1 U2. That is indicates first nodal element, that it is consists of 2 nodes. Then respective nodal displacement is U1 U2 equal to your geometric force condition F1 F2 plus rho g AL by 2 1 1. In this case, the body force is not specified. It means the density of the material is not given. Therefore, we neglect the body force step. Then we have to apply your area of this first element is to be 250 millimeter square. Then Young's modulus value is also specified in the problem. Then E is equal to 200 into 10 power 3 Newton per mm square divided by length of the element is 150 millimeter. We see that element number 1 consists of node 1 and 2. That node 2, they specified nodal force is to be 300 kilonewton. That means 300 into 10 power 3 Newton. We already assigned here 300 into 10 power 3 Newton for nodal location 2. This is towards a positive direction of x-axis. Therefore, we consider it a positive. Then we will get equation number 2. The top red color indicates 1 and 2. It will associate with your nodal number for element number 1 and for element number 1. So here I already assigned that force at location 2 is 300 into 10 power 3. So we will go and derive a finite element equation for element number 2. We need not to again assign the same force because this is a geometric loading condition. If assign any one node, we need not to assign further. Okay, if you consider element number 2, neglect your body forces, then again AE by L, the values areas to be 250 millimeter square. Then Young's modulus value specified 200 into 10 power 3. Length of the element also 150. Then 1 minus 1 minus 1. Element 2 consists of node 2 and 3. The respective displacement is U2 and U3. Here it will be U2 and U3, not U3 and U4. Then equal to, because here the nodal forces at the nodal location 2 is, the problem is specified 300 kilonewton. We already assigned in the previous equation, so you need not assign here. Okay, then we will get equation number 3. The top red color indicates your nodal number of respective elements. Then consider element number 3. Here also you neglect body forces. Element 3 consists of node 3 and 4. The respective nodal displacements U3 and U4. Then the area of the element is to be 400 mm square. Young's modulus value is 200 into 10 power 3. Length of the element is 300 millimeter. Then we will get 10 power 5 by 3. 8 minus 8 minus 8 8. U3 and U4 equal to 0. Then 3 and 4 indicates your nodal number of respective elements. From equation 2 and 3 4 we will assemble, we will get a finite element equations. So here the given structure is described into 3 elements. That means consist of 4 nodes. Therefore, each node having 1 degree of freedom. Therefore, the 4 unknowns. Therefore, the size of the stiffness matrix is 4 cross 4. That's why the top red color indicates 1, 2, 3, 4 in red. It will be indicates your nodal numbers. So based on that, we have to assemble. We will get a global stiffness matrix. We see that what is the combination of the 2, that's a 2 value is a 20. How we will get this 20? We go for equation 3, the 2 combination is 10. Then in equation number 2, the 2 combination is a 10. Then 10 plus 10, we will get 20. The same way we have to assemble. We will get your global stiffness matrix. Then your nodal displacement is U1, U2, U3, and U4. Then the force specified at a geometric loading condition is node 1, there is no external force, that will be 0. Then node 2, it will be a 300 kN positive x-axis, therefore 300 into 10 power 3 Newton. Then node location 3 and 4, there is no external loading condition. That's why I specified 0, 0. Then you have to apply your essential boundary condition. What is your essential boundary condition? In these physical structures can be described into 3 elements. Then nodal location 1 is fixed, as well as nodal location 4 also fixed support. Therefore, it will offer some reactive forces that at this nodal location the nodal displacement are 0. Therefore, node 1 and 4 is to be fixed. It will offer reactive forces that the respective displacement is 0. This is an essential boundary condition, because at the boundary it is specified boundary values in terms of your field variables or dependent variables. Here our ultimate aim is we currently find out the nodal displacement of the respective nodal locations. Therefore, the nodal displacement U1 is a field variable, that is a dependent variable. So U1 as well as U4 becomes 0. That's why in the equation 5 I replaced U1 as well as U4 value 0, the respective force matrix. Then we have to replace the reactive force R1 as well as R4. Whenever you apply your essential boundary conditions, then we have to remove the respective rows and columns. Then above global stiffness matrix can be reduced into 10 power 5 by 3, 20 minus 10 minus 10, 18, U2, U3 is equal to 300 into 10 power 3, 0. Then we have 2 unknowns. Then we will get 2 equations while solving these equations 7 and 8. Then we will get the values of U2 and U3 values. Then how we will calculate your element stress? Then we have to, according to Hooke's law, the stress is induced to the material directly proportional to strain. Then E sigma is equal to E times into du by dx, where du by dx is nothing but your strain. If we consider element number 1, that is what is a du value, that means U2 minus U1, where U1 is to be fixed, then once U1 becomes 0, we already find U2 value. Then we get sigma is equal to young small is a 2 into 10 power 5 Newton per millimeter square into what is the value of U2? It is a 0.623 millimeter minus U1 0 divided by length of the element is to be 150 millimeter. We will get 830.6 Newton per mm square. The same way you have to calculate stress for element number 2. Sigma is equal to E into du by dx. Then E into du by dx value du by dx, that can be written as U3 minus U2 by L. Then we have to substitute all the values. We will get minus 369.33 Newton per mm square. The same way you have to calculate stress for element number 3. Sigma is equal to E into U4 minus U3 divided by L. Then we will get minus 230.67 Newton per mm square. Now how we will obtain the reaction force? We go for equation 6. From that equation, we have to apply our nodal displacement. Then your first row of your stiffness matrix into your nodal displacement, it will give R1 value. Then fourth row of your global stiffness matrix into your nodal displacement vector, then we will get R4 value. We substitute, then we will find the value of R1 and R4 value. We assume the R1 R4 is towards the positive direction, but we will get the here answers to be negative. Therefore, your assumed direction is wrong. It will act opposite to your assumed direction. In this case, we assume towards the positive direction of x-axis, but we will get the negative answer. Therefore, the original direction of R1 R4 is to be opposite to your assumed directions. Then we look at problem number 2. For a taper bar of uniform thickness T is equal to 10 millimeter, as shown in figure. Find the displacement at the nodes by forming into 2-element model. The bar has a mass density of rho is specified 7,800 kg per meter cube. Young small c is equal to 2 into 10 power 5 mega Newton per meter square. In addition to self height, the bar is subject to a point load of 1 kN at its center. Also determine the reaction force at the support. Therefore, the given problem is to be a tapered bar problem. It means the cross section of the bar keep on varying with respect to distance. That we have to derive the finite element equation for a bar having uniform cross section only. Therefore, this stepped bar we have to the taper bar we have to convert it into stepped bar. Then we have to calculate our nodal area. The node 1 having a width of 80 millimeter, the thickness to be 10 millimeter. The nodal area A1 is equal to 800 mm square. The same way, the nodal number 3, the area of nodal values 40 into 10, 40 into 10 is to be 400 mm square, not 800 mm square. Then A2 is equal to, that means this is specified at the center value. Therefore, 80 plus 40 divided by 2 into 10, we get 600 mm square. Once we know the nodal value, then we have to calculate elemental area, because the element 1 consists of node 1 and 2. Therefore, node 1 having 800 mm square, then node 2 having 600 mm square. We will take average value, we get 700 mm square for element 1. The same way, element number 2, it is consists of node 2 and 3. Then the nodal area is 2 is 600 mm square. Then 3 is 400 mm square. We will divide by 2, we will get 500 mm square. Therefore, the given taper bar we converted into stepped bar problem. We see that this is your taper bar is converted into stepped bar into 2 elements, where element 1 having area of 700 mm square, element 2 having area 500 mm square. Now the problem is converted into stepped bar problem, where element having uniform cross-sectional area. Then we have to apply our finite element equations. We already derived the finite element equation. In this problem, density of the material is given. Therefore, we take into account of your self height also. Consider element number 1. The area is to be 700 mm square into Young's modulus value specified 2 into 10 per 5 Newton per mm square. Then length of the element is to be 150 millimeter. 1 minus 1 minus 1 1. Element 1 associated with nodal displacement u1 u2 z. Then equal to your nodal force. At a nodal location 1, there is no external force. Then your nodal location 2 is the external force of 1000 Newton is specified. It is, we assume in this problem towards the downward direction, I assume is a positive. Plus your density of the material is specified 7800 kg per meter cube. G value is 9.81 meter per second square. Then areas to be 700 mm square. Here all are we substitute in the meter. That's why we use substitute 700 into 10 power minus 6 into distance length of the element is to be 150 millimeters. So we substitute in the meter 0.150 divided by 2 1. Then we will get 10 power 6 by 15, 14 minus 14 minus 14, 14. Nodal displacement u1 u2 is equal to 4.017, then 1004.017. It is equation number 2. This is your finite element equation for element number 1. It is consists of node 1 and 2. That's why the top red color indicates 1 2 1 2 is to be a respective nodal locations. Here we already assigned the 1000 Newton for node 2 in element 1. So while develop a finite element equation for element number 2, we need not to assign again 1000 Newton, because it is geometric loading conditions. You have to assign any one locations. So consider element number 2 having areas to be 500 mm square into Young's modulus value 2 into 10 power 5 Newton per mm square. Length of the element is to be 150 millimeter. Then element 2 consists of node 2 and 3. Then in this case, we already 1000 Newton is assigned for element number 1 in the nodal location 2. Therefore, again we need not to assign here. Then we have to take into care of your body forces. Then we will get equation number 3. 10 power 6 divided by 15, 14 minus 14 minus 14, 14. u2 u3 equal to 2.869, 2.869. While assembling equation 2 and 3, we will get a global stiffness matrix. I already told that how to assemble a global stiffness matrix. Here we consist of 2 elements, each element having 2 nodes. Therefore, the total node is to be 3, each node having 1 degree of freedom. Therefore, the size of the stiffness matrix is 3 cross 3. Then we will obtain equation number 5. Then in this case, node 1 is to be fixed. Therefore, you have to apply very essential boundary condition at a nodal location 1. That means u1 equal to 0, where the fixed support associated with some reactive forces. Initially, we assume r1 is downward direction. Therefore, in this problem, we assume the downward direction is to be positive. Then equation 6, we have to apply an essential boundary condition at nodal location 1. Therefore, we remove the respective rows and columns. then we will get simplified your finite element equation. From that equation, we have two unknowns, then we have two equations. While solving these two equations, we will get U2 and U3 values. Once we find out U2 and U3 value, then we have to calculate your element stresses. For element stresses, how can you calculate? E is equal to, sigma is equal to E times du by dx. We have to apply this equation. Then we will get the element stress for element 1 and 2. If we go for element number 1, the sigma is equal to E into U2 minus U1 divided by L. Then we will get 830.6 Newton per mm square. The same way we have to calculate element stress 2 also. Here this, forgot to tell you, we have to substitute this U2 as well as U3 in these values 1.081 into 10 power minus 3 millimeter. Then U2 also 1.084 into 10 power minus 3 millimeter. Only we have to substitute. This is a previous problem value. We have to substitute here. We have to substitute the exact value what we obtained from previous slide. The same way you have to calculate the reactive forces from equation number 6. Then I gave one assignment problem, that it means find the axial force in the spring bar assembly as shown in figure. Assume K is equal to 1 lakh LPS per inches, that L equal to 30 inches. The force applied at a rigid body is to be 15,000 LPS. For steel, the Young's smallest value is specified. E is equal to 30 into 10 power 6 pounds per square inches. Then area is to be 0.5 inches square. Therefore, the aluminum bar E is equal to 10 power 7 pounds per square inches. Then A is equal to 1.2 inches square. If you see that it is element 1 is consists of a spring element, then if we already derived the finite element equation for bar element, that means what is a stiffness matrix? K is equal to AE by L, 1 minus 1 minus 1, 1. This equation AE by L indicates your stiffness. That means load produced per unit deflection is called as a stiffness. And AE by L we can replace it as a spring constant K for spring element. Therefore, the stiffness matrix for spring element is nothing K times 1 minus 1 minus 1, 1, where K is the spring constant or spring stiffness. Therefore, element 1 having a nodal 1 and 2, where it is a spring element. We know the stiffness matrix K into 1 minus 1 minus 1, 1. K value is already specified. This bar is to be reached if you applied some external force at nodal location 2. Due to application of this external force, the steel as well as aluminum bar is subject to axial displacement. Therefore, we have to consider steel as a element 2. It is also consists of node 2 and 3. Then if you go for aluminium, it is also consists of nodal location 2 and 3. Therefore, we have to top right the red color 2, 3, 2, 3. Then same way we have to assemble, we will get a global stiffness matrix. Then after that, we have to apply your essential boundary conditions. What is your essential boundary condition here? There is node 1 is fixed, therefore U1 also 0. Then node 3 also fixed, U3 also 0. We are only, we have to find out your U2 values. Once you find out U2 value, then how we will calculate the stresses induced in the steel as well as aluminium. That means sigma is equal to E into du by dx, where du by dx can be written as U3 minus U2 divided by length of the element. Length is specified at 30 inches. The same way you have to calculate aluminium. Once you find out stresses induced in steel as well as aluminium, then we have to calculate forces induced in the steel as well as aluminium. Then how we calculate? Then we know that stress equal to force by area. If you want force, means force into stress into area of the steel, or if you want to find out aluminium, then stress is induced aluminium into area of the earth. Thank you.